Hi students, in this video we continue solving few remaining problems on dual nature of matter and radiation. Okay, so here we go. The question is like this: the light of wavelength 5000 Armstrong falls on a photosensitive plate with photoelectric work function phi naught. One is 1.9 electron volt. The kinetic energy of the photoelectron emitted will be, okay, your options are A 0.58 electron volt, option B 2.48 electron volt, option C 1.24 electron volt, option D 1.16 electron volt. So we'll solve this now. So we have to find the kinetic energy, so directly we'll go with the formula. Kinetic energy K maximum is equal to hc by lambda minus phi naught, right? So since options are in electron volt, we'll keep this also in electron volt, and the given thing is phi naught is also in 1.9 electron volt. So and it is in Armstrong. You know the direct formula, that is we can take 12,375 or 12,400 Armstrong directly. Okay, so this divided by 5000 Armstrong, so electron volt minus 1.9 electron volt. So just for further simplification, I'll write this is equal to, but this is approximately equal to 12,400 divided by 5000 electron volt minus 1.9 electron volt. So this two zeros get cancelled. So 124 divided by 50, that approximately if you calculate, you are going to get so 51s are 52s are 150. Okay, this is approximately take 125, then it is obviously 2.5 times, right? But it is 124, so nearly it is 2.48 times. Hope you got this. 125 by 50 is 2.5, so 124 divided by 50 is 2.48. I am taking electron volt minus 1.9 electron volt, so this will be 0.58 electron volt. Since we know this directly, instead of multiplying h, c, everything, so we know this directly and approximation, so we can take this answer directly. Okay, so option A is the right answer. Hope you got this. Okay, so next, right, so we'll go to the next question. Look at the next question we have. When photons of energy h nu falls on aluminium plate of work function E naught, okay, so photoelectrons of maximum kinetic energy K are ejected. If the frequency of the radiation is doubled, then the maximum kinetic energy of the ejected photoelectrons will be. So I had to read the question properly, understand the question properly. So they have given one particular kinetic energy and we have to find, okay, so if the frequency is doubled, then what will be the new kinetic energy? Okay, so again we'll go to the kinetic energy formula. So K is equal to h nu minus phi naught is the standard formula we know, right? And this is for the first one. Okay, now if the frequency is doubled, okay, so then K dash L, right, the new kinetic energy K dash is equal to, okay, frequency is doubled means 2 times frequency, so I'm writing 2 h nu, right? So minus phi naught as it is, right? So now here simplification I will do. This implies phi naught is equal to h nu minus phi naught, correct? H nu minus K, because I am sending this. So I can substitute phi naught here. This is 2h nu minus, in the place of phi naught I can write h nu minus K, correct? So I can write 2h nu minus h nu plus K. So 2h nu minus h nu is h nu plus K. So it means K dash is equal to h nu plus K, correct? So now, yeah, so it means the new kinetic energy will be what? So in this given option B is the right answer. Clear? Okay, next we'll go to the next question. Look at the question. the incident photon involved in photoelectric effect experiment. Okay, so what happens to that? Will that completely disappears, comes out with an increased frequency, come out with an decreased frequency, or come out with a change in the frequency? So increase or decrease, anyway it is change in the frequency. So what is the possible answer now? Yeah, it's actually, it's going to completely disappear, because you know when the plate is illuminated with the light, okay, E is equal to h nu. So this frequency, okay, this photoelectric incident light photon, this is going to utilize for the work function, and remaining will be utilized for kinetic energy. Okay, so the part of the energy is utilized here, okay, and the remaining will be electron is coming out, not the photon. So it means the photon will be completely disappeared. Okay, photon is not coming out because it is not a reflection, but rather it is ejecting the electron. Okay, so it means photon is, it is like, okay, it is going to destroy itself to remove the electron. Got it? So it means completely disappear is the right answer. Okay, we'll go to the next question. Right, read the question properly. The the threshold frequency for metallic surface corresponds to an energy of 6.2 electron volt, and stopping potential for a radiation incident on this surface is 5 volt. The incident radiation lies, okay, so it means we have to find in which region it is falling. Okay, it means you have to find the lambda, then we should know where the lambda is lying, right? So we'll solve it now. This requires a lot of time maybe, so keep solving, myself also will be solving, right? Okay, so again we have to find lambda. So we have the formula, they have given the threshold frequency and voltage and all. Again we'll go with the K maximum formula. K max is equal to hc by lambda minus phi naught is the standard formula we should use. So we want the lambda, so let me take this hc by lambda this side, means K maximum plus phi naught, because this, if I take that side, okay, that is 5 plus, right? So it means now K maximum they have given, okay, and phi naught also they have given, right? So K maximum is 5 electron volt, okay, because stopping potential they have given. So we know that K maximum is equal to E V naught. If V naught is 5 volt, then K maximum is equal to 5 E electron volt, right? So here I can write 5 electron volt plus phi naught is how much? Phi naught is 6.2 electron volt, okay, because here energy is given, right? Now the total is 11.2 electron volt hc by lambda. Now we have to find lambda, right? Therefore lambda by hc is equal to 1 by 11.2 electron volt, right? And do you remember the formula? This is nothing but lambda is equal to hc by 11.2 electron volt, okay. So hc is how much? hc if you multiply it, if it is in electron volt, that is 1000, approximately 1400 electron volt divided by 11.2 electron volt. This is the standard formula, okay. So this is nothing but electron get cancelled, and what I do is 1 2 4 0. I'm going to, instead of taking 2 zeros, I'm going to take this, I'll make it as, instead of 11 I'm going to make it 1.12. So I have removed 1 0 here also. I have taken the point system here, so that is correct, no problem. So now if I do this calculation, okay, so we had to do calculation like this, 1.12 and all. So you're going to get approximately like so we get around 1107 times if you get, you'll get the answer. Okay, anyway, so approximately I have done, because see, this is, if you multiply 10 times, there is one plus 11 point something will get. Okay, so here the numerator is 12,000, I mean 1240. Obviously it is, we should get this answer nearly. Okay, it is anyway 110 something like this, around this value you are going to get. Okay, so Armstrong means in 10 power minus 10, correct. So you can keep this as in nanometer also if you want to keep, right. And this answer, Armstrong or nanometer, whatever, but this lambda, you should know how, where it exactly lies. Okay, and for this let me write few important things. For radio waves, radio wave, microwave, IR waves, visible, UV, X-ray, gamma ray, right. So here basically, you know, for visible ray, you know, this is from 700 nanometer to 4000 nanometer. Okay, and for UV it is 400 nanometer to 1 nanometer. So if you go here, it is around 1 millimeter to 700 nanometer. Okay, so where this lies, and then so you can write. Okay, further if you want to write, I'll write it. 0.1 meter to 1 millimeter. This will be more than 1 meter, 0.1 meter. Okay, and this will be 1 nanometer to 10 power minus 3 nanometer, and it will be less than 10 power minus 3 nanometer. So these things you should be knowing. Okay, if it is there in your mind, and it is easy to calculate. So here we get lambda is equal to 110.7 nanometer. This lies here, correct. So the options are, this is ultraviolet, this is ultraviolet. Okay, so other things are not possible, so you should remember this. So this is the right answer. Option D is the right answer. Hope you got this. A lot of calculation is involved, but if you remember these things, and the quick calculation will lead to quick answer, right. So we'll move to the next question now. Right. Okay, read on the next question. Read it out. Okay. A photoelectric surface is illuminated successfully by monochromatic light of wavelength lambda and lambda by 2 if the maximum kinetic energy of the emitted photoelectron is in second case is 3 times that in the first case. The work function of the surface of the material is, so you have to find the work function. Work function means phi naught or W naught. If you find that, you'll get the answer. Okay, so we'll see now. Again we'll go with the formula. K max is equal to hc by lambda minus phi naught. Okay, standard formula, right. So in the first case, let me write first case, k1 is equal to hc by lambda minus phi naught. But in the second case, k2, this is 3 times k1 it seems, right. So it's 3 times k1, but here the lambda is divided by 2 because he's here the given thing. So it means here I can change the formula, lambda hc by lambda by 2, right. So here only lambda, here lambda by 2 minus phi naught. It means this is 3k1 is equal to 2 hc by lambda minus phi naught, correct. Now you substitute. In the place of k, I can substitute this. It means 3 hc by lambda minus phi naught is equal to 2 hc by lambda minus phi naught. Okay, so if you calculate this, okay, 3 times and all, so approximately finally we're going to get the answer here. I'm going to write it here. Okay, hc by lambda is equal to 2 phi naught we're going to get. So it means phi naught is equal to hc by 2 lambda. So which is the right answer? Option D is the right answer. Hope it is clear. Okay, so we'll go to the next question now. Please read the next question. Among the following 4 spectral regions, the photon has the highest energy in. So you should find which is having highest energy, right? Is it infrared or violet or red or blue? Okay, we'll see. Now we know E is equal to hc by lambda. It means E is inversely proportional to lambda wavelength. So now we know we should now understand either lambda infrared is greater than lambda red, greater than lambda blue, which is greater than lambda violet. Okay, for lambda violet, this is 400 nanometer. Okay, and red, 700 nanometer, because this is nothing but visible, right? Visible ray. Okay, red to blue. Okay, the VIBGYOR. Okay, violet, blue, indigo, and all those things, and after that the infrared will come. So this infrared is basically from 1 millimeter to 700 nanometer. So which is greater? This will be greater, obviously. Okay, in case of the wavelength, I'm telling. If wavelength is greater, if wavelength is increasing, energy is reduced. So which is the greater energy in this case? The least wavelength will be having greater energy. It means the violet will be having more energy when compared to the infrared or red or blue. Correct? So option B is the right answer. Hope this is clear. Option B is the right answer. Okay, moving to the next question. Read out please. When radiation of wavelength lambda is incident on a metallic surface, the stopping potential is 4.8 volts. If the same surface is illuminated with the radiation of doubled wavelength, okay, here also the wavelength, second wavelength is doubled, then the stopping potential becomes 1.6 volts. Then the threshold wavelength for surface is. Okay, so we'll see that. This is a quite bigger one, right? Okay. Okay, so we know that K maximum is equal to h nu minus h nu naught. That can be written as h c by lambda minus c by lambda naught. Correct? Okay, so we know that K maximum is nothing but E V naught is equal to h c. I'll take common 1 by lambda minus 1 by lambda naught. Correct? So here V naught is equal to hc by E 1 by lambda minus 1 by lambda naught. That will be equation number 1. Now we'll go with the different cases, given cases. Okay, so case for case 1. Okay, so P naught they have given 4.8, okay, is equal to hc by E 1 minus lambda minus 1 by lambda naught. Okay, so let it be equation number 2. Now for the second case, case number 2, potential is 1.6, okay, is equal to hc by E minus 1 by this is lambda is 2 because see they have written it is double the wavelength, so 2 times the wavelength they had, right? So minus 1 by lambda naught. Okay, this lambda naught will remain same. This is equation number 3. Now do one thing, equation number 2 by 3. Okay, so we'll do equation number 2 by 3. This, here we go, 4.8 divided by 1.6, hc by E get cancels, then finally this will be lambda. Okay, if we take this LCM, okay, so this will be lambda naught minus lambda into lambda naught divided by lambda naught minus 2 lambda into lambda naught. Okay, so these things get cancelled and finally we'll remain with 2 into lambda naught minus lambda divided by lambda naught minus 2 lambda, correct? So after cross multiplication we get this is 4.8 by 1.6 is 3 is equal to 2 times lambda naught minus lambda by lambda naught minus 2 lambda. Further simplification will leads to the answer lambda naught is equal to 4 times lambda. Okay, so this is the final answer. So it means option B is the right answer. Clear? Now we'll go with this one more problem, the last problem of this video. Okay, look at the problem, read it clearly. The source of light is placed at a distance of 50 centimeter from a photocell and stopping potential is found to be V0. Stopping potential is found to be V0. If the distance between the light source and the photocell is made 25 centimeter, it means earlier it was 50 and now it is reduced by half, 25. The new stopping potential will be. Okay, so it is very easy answer, no much of calculation, because see, the stopping potential is independent of the intensity of the light and hence independent of distance. Okay, so stopping potential is not dependent on the intensity. So we know that intensity is directly dependent on distance, because it is not directly. Intensity is 1 by d square, right? Okay, so but now stopping potential is in stopping potential V0 is not dependent on I. It means it is not dependent on d square also or d. So it means it will remain the same. It means if earlier it is V0, then the new stopping potential also V0. So option B is the right answer once again. Yes. Okay. Now remaining questions we will solve in the next class. Thank you.